Alright, hi guys. Today we're going to be talking about writing rational function equations. In our last videos, we talked about given a rational equation, specifically the graph of a rational equation, how could you find the horizontal and vertical asymptotes? How could you find the domain and the range, and also the transformations? We are going to expand upon that with taking those same graphs and writing standard form rational equations from those graphs. So notice here you have this function y equals a divided by x minus h plus k. We are going to be doing a little bit with a. We're primarily going to be focusing on h and k. We have used transformations with h and k already this year. We also may have called them C and D, depending on the unit, but it's the same idea. When you write the equation of a rational function, you need to identify a few key features that are different or vary from the equation of the parent function. So A is the dilation factor. H is the horizontal movement. So this is going to go left or right. But the key thing here is that you always want to think about the horizontal movement h as opposite. Notice how in the equation itself there's a minus, so it's opposite of what you would think. And then the vertical is going to be up or down. And the horizontal movement as well is going to be directly related to the horizontal asymptote. And the vertical movement k is going to be directly related to the vertical asymptote. So all of these things are very much connected. This is our generic standard form function for the function 1 over x, the parent function 1 over x. We can also do 1 over x squared, which is very similar. It would just be y equals a over x minus h squared plus k. But ultimately that's basically the same idea. So we've got the graph of 1 over x here. Notice that it has the asymptotes already drawn in here. The vertical asymptote is x equals 0. That's right here. Right here on the y-axis. The horizontal asymptote is y equals 0 right here on the x-axis. And the point where the horizontal and the vertical asymptotes intersect is going to be our point hk. That is our special point that we use to help us find our transformations and help us to write our equation. In this case, they meet at the origin, the point 0, 0. So that is going to affect our equation. They're also talking here about key locations at 1, 1 and negative 1, 1. Because of the locations of those, there hasn't been a dilation. We're pretty much just gonna, for looking at a graph, gonna focus on not having a dilation, with a being 1. And when we get to the very end of these notes, we'll talk about how you can have an equation and state the transformations, and then we'll talk about dilations other than 1. So you can see that this point here, 0, that's your h. This point 0 here, that's your k. The h goes here, the k goes here, and if you simplify, it's 1 over x. So this is our most basic parent function here, 1 over x. Same idea for the next one, 1 over x squared. Again, you have your vertical asymptote at x equals 0, your horizontal asymptote at y equals 0. They again intersect at 0, 0, so that is hk. And if you look at the equation down here, h is 0, k is 0, and if you simplify, you get 1 over x squared. Again, here they're talking about the dilations. because this is at 1, 1, and this is at negative 1, 1, the a value is 1. Again, for when we're talking about graphs, we're going to specifically be just focusing on ones that have an a of 1. Only when we get to equations themselves will we be doing other things. So let's take a look at this first example here. This is really taking what we did in last week's material and adding to it. So first thing it wants to know is the vertical and horizontal asymptotes. So I am going to go ahead and put those into my graph. And remember, the asymptotes are the lines that the graph gets closer and closer to but never touch. All of the rational equations, all the rational functions that we are going to be talking about are always going to have a vertical asymptote and a horizontal asymptote. In this case, this is a transformation of the parent function 1 over x. We can see that this vertical asymptote has been moved to x equals negative 3, where the horizontal asymptote is the same as the rational function, y equals 0. So therefore, the domain here would be x does not equal negative 3. The range would be y does not equal 0. And then here's where the equation part comes in. We would have y equals, a is 1, and then we can see the point where these graphs intersect right here. That point is right here at negative 3, 0. That is going to be your h and your k. So it'll be x minus negative 3 plus 0. And you can keep it like that, but it's not really ideal. You'd want to simplify at least a little bit. Minus a negative is the same thing as plus, so this would be 1 over x plus 3, and then you don't really need that plus 0 there because it is a 0. So this is my equation. In the next example, we're again going to go ahead and find our asymptotes. So we've got our vertical asymptote here on the y-axis, x equals 0, but our horizontal asymptote has moved. So our vertical asymptote is x equals 0. Our horizontal asymptote has turned into y equals negative 2. And so that is going to affect our domain, our range, and our equation. So first thing, we'll talk about the domain. It would be x does not equal 0. And the range would be y does not equal negative 2. And then for the equation, we need to find the point here where the asymptotes intersect. That point is going to be at 0, negative 2. That is my hk. So y equals 1 over x minus 0 plus negative 2. And again, I'm going to simplify this to y equals 1 over x, because that 0 can go away. And then my plus a negative is the same thing as a minus, so minus 2. All right, and then for number 3, again, I'm going to go ahead and put in my asymptotes here. My vertical asymptote has shifted from my parent function. My vertical asymptote here is x equals 3, and my horizontal asymptote here is y equals negative 4. And this again will affect my domain, range, and equation. So in this case, my domain would be x does not equal 3. My range would be y does not equal negative 4. And then for my equation, we will look at the point where my asymptotes intersect. That is this point right here. So that is 3, negative 4. So that is my hk. So y equals 1 over x minus 3 plus negative 4, or 1 over x minus 3 minus 4. Please notice here, and this will be the same when we go to the examples of 1 over x squared, but please notice here that the h you change the sign, and then the k you do not change the sign. That is the most important thing with writing the equation. Alright, the next three examples are all based off of the parent function 1 over x squared. I'm going to start these the same way. I'm going to put in my asymptotes here. And so my vertical asymptote in this case has changed from my parent function. Now it's x equals negative 3, but my horizontal asymptote is still y equals 0. So my domain here would be, x does not equal negative 3, different color, but that's okay. The range here, y does not equal 0. And for my equation, again, I'm looking for this point where my asymptotes intersect. That point in this case is negative 3, 0, x comma y, which is hk. So y equals, now this is a parent function of 1 over x squared. Notice how the branches are at the top here. So this would be 1 over x minus negative 3 squared plus 0, which when I simplify turns into 1 over x plus 3 squared, because the plus 0 doesn't have to be there, and then minus a negative is a plus. All right, and in example 5, we have this asymptote here and here. So our vertical asymptote is now on our y-axis, x equals 0, but our horizontal asymptote has shifted down, y equals negative 2. Our domain now, I just realized I made a mistake on the last one, guys. Let me just go back real quick. So the range here, I apologize, going back to number 4. Real quick, the range here is not correct. The range in this case, sorry, there's nothing, it's a 1 over x squared, so there's nothing here below this horizontal asymptote, so it's actually, the range should be y is greater than 0. I apologize. Not y does not equal 0. That would be if it were a transformation of 1 over x, but since it's a transformation of 1 over x squared, the range is different. And we'll also see that difference in range in number 5. So the domain here will still be x does not equal 0, but the range will be y is greater than negative 2. This does not affect the equation. So for the equation, we are going to find the point where my horizontal and vertical asymptotes intersect. That's 0, negative 2, which is my hk. So y equals 1 over x minus 0 squared plus negative 2. When I simplify, I get 1 over x squared minus 2. And then for number 6, we will go ahead and put in our asymptotes here. X equals 4, y equals 1. Vertical asymptote, x equals 4. Horizontal asymptote, y equals 1, and then we'll talk about domain and range. For our domain here, this would be x does not equal 4, but our range, since this is a transformation of 1 over x squared, the range would be y is greater than 1. And then for the equation, we're looking for the point where the asymptotes intersect. That point here is at 4, 1, that's my hk. So I get y equals 1 over x minus 4 squared plus 1. And actually, there's nothing to simplify there. That is my final equation. All right, so that is how you find the vertical, horizontal asymptotes, domain and range, all of that from last week as well. And now adding this last piece of finding the equation of transformations of parent functions from the graphs of 1 over x and 1 over x squared. Now we want to do is we just want to talk about those transformations. So again, this is building on what we did last week, but now we're adding dilations to that. You can tell if something has been dilated if the a value is not 1. And we have talked about this earlier in previous units, just not with this specific type of function. But if you go ahead and you look at number 1 here, all of these, it says use the equation of the function to describe how the graph has been transformed from its parent function. So there's again 3 different things that could happen. You could translate up or down, you could translate left or right, or you could dilate. In this case, number 1, there is just a 1 here at the top, so it's not a dilation. I do see a -3 here. That's going to be my h. And then there's nothing here, so there's no k. So what that means, if my h has been altered here, we change the sign to help us determine if it's left or right. So in this particular case, it was a minus. So that means that we're going right. So we are the graph has been translated right 3 units. Okay? Minus is right, plus is left for h, and then for k, it does not change from what you would typically think. Positive is up, negative is down. If you look at number 2, this time it's a transformation of 1 over x squared, but again, it's still in the h here. This is the only transformation that has occurred. So this is +4, which means that this graph has been translated left 4 units. Translated left 4 units. If you look at number 3, there's no h, there's no k, but now we have a different a here. It's a 5. So what that means is that my graph has been dilated by a factor of 5. You just take that number that has been replaced here, and that's what it's been dilated by. Same idea if you look at number 4. Again, we've got x squared here instead of x, but it's the same idea for the transformations, but we've got this 8 here instead of a 1 in the numerator, so that means that it has been dilated by a factor of 8. All right, and once we get to 5 through 8, we can see that there's more than one transformation happening here. So if you look at number 5, you can see that you have this +4 here. That +4, again, it's the h, so it's opposite. And it's left or right. In this case, it's opposite, so plus would mean left. So translated left 4 units. And then you've also got this +5 going on here. That is your k. If you are adding something for your k, that means that it's up. So this is translated up 5 units. So both of these together make your transformations for number 5. For number 6, you've got this -6 here. That means that the graph has been translated. Since it's the h, it's left or right. -6, we do opposite, so that means it's right. Right 6 units. And then we've got this -4 here. That is our k. When that is a k and it's negative, that means down. So this is translated down 4 units. Here we've got a 3 in the numerator instead of a 1. So what that means is that this, for number 7, this equation has a dilation by a factor of 3. And then here, minus 7. That is our K. So just like number 6, that is translated down, but this time 7 units. And then finally for number 8, we actually have all 3. So this 2 here in the numerator instead of a 1 means that my equation from the parent function is a dilation or dilated by a factor of 2. This minus 4 here as our h makes this graph translated right 4 units. And this plus 9 here, our k, makes the graph translated up 9 units. Okay, so hopefully you're able to follow along with those notes. Mostly we're just adding on to the stuff that we worked on in our last week of distance learning with rational functions. Later this week, we will also put out practice problems as well as a video going over those practice problems. But please try the practice problems yourself first. Okay? Have a wonderful day.